In this video, I'm only going to talk about standard error of kurtosis in a relatively brief way. I want you to take away a couple of key points though. One is, just like the standard error of skew, standard error of kurtosis is based exclusively upon sample size. So unlike most other standard error estimates, which incorporate the standard deviation or variability or variance in some way, skew and kurtosis are relatively unique in that they don't. They're based exclusively on the sample size. And this formula here actually includes the standard error of skew first, which is then manipulated to yield the standard error of kurtosis, which in this case corresponded to a rather small value of 0.068. Again, it's small because the sample size is so huge. 5,225 individuals reported their annual earnings in this study. I had to identify the critical t-value, the t-distribution, with 5,224 degrees of freedom. Again, the sample size is so large, it's approximating the z-distribution extremely closely, and that's why it gave me a t-value of 1.96, which is exactly the same z-value I would get from the z-distribution with the same level of probability, as in 95% of the distribution, or stated alternatively, 5% outside the specification at the ends of the tails of the distribution. And that gave a value of 1.96, which I multiplied against the estimate of standard error, and with that product, which was equal to 0.133, so when you multiply 1.96 by 0.068, you get 0.133. Let's just verify that. 1.96 times 0.068 yields 0.133. And that's why I use that value to subtract from the kurtosis estimate of 7.78. That gave a value of 7.647, so it's really very close to the point estimate of 7.78. And the 95% upper bound is 7.913. So again, the range and the confidence intervals is very narrow because the sample size is so huge, and we can probably confidently state that the kurtosis in the population, as in the whole entire US population that earns money, that it's very likely a positively kurtotic distribution.